way, we'll get started. So 802.11n is now known as Wi-Fi 4. The earlier 802.11a,b,g, I assume, are Wi-Fi 1, 2, and 3. The modulation it uses is orthogonal frequency division modulation, which, by the way, if you run WinLink, is also used by VARA. And uses multiple subcarriers, and each one of them carries some modulation, some data. The data stream is split up at the transmitter and recombined at the receiver. Beyond that, you'll have to go to Wikipedia. The information gets very dense very quickly, but just know it's OFDM and has bunches of carriers, and they all carry separate data. This screen looks pretty intimidating, so let's walk through it slowly. On the upper left, it says MCS index. That's modulation and, let me move this bar. Oops, hang on. Modulation and coding scheme, MCS, that's all it means. And if you've ever run PSK 31, it's BPSK, biphase shift keying. There's a QPSK, which is quadrature phase shift keying. And down there is QAM, it's quadrature amplitude modulation. And there's various modes of that. And just like your old 56K modem, 802.11n negotiates from the fastest to the slowest data streams possible, and it works its way down from the fastest to the slowest. In red there, I've got encircled 20 megahertz channel. This would be what we would use if you're using a 20 megahertz channel on 5 gigs. And you can see I've got the 400 nanosecond guard interval column circled. They switched from 800 nanoseconds to 400 nanoseconds, I don't know, 2 or 3 years ago, and got a little speed bump from it. And you can see as we move up in MCS indexes from 0 to 15 on the left, so 16 total, the absolute fastest modulation data rate you can get on a 20 megahertz channel is 144.4 megabits per second. And this is on a 20 megahertz channel. A number of years ago, before my county switched from 20 megs to 10 meg bandwidth to get more channels, we did in fact see that a few times on a very, very short length with a very, very short distance with high gain antennas on both ends, but typically it would be less. You can see on the left, I've got a rectangle, red rectangle around 0 through 7. Those are the ones you get with a 10 megahertz bandwidth. And you can see the max there is 72.2, half of it. So it's just good to know. I'm going to talk about MIMO, which is multiple input, multiple output. We all talk about it. What it's used for is to send more data than you'd think you could on the same channel by sending 2 data streams in our case. It says they're exploiting multipath propagation. It does, but that's not its main advantage. Its main advantage is SDM, spatial division multiplexing. So what that means is, in our case, our spatial diversity is polarity diversity. We use 2 channels, or two data streams, one vertically polarized and one horizontally polarized. On the same channel, the transmitters transmit simultaneously, vertically polarized and horizontally polarized, each transmitting part of the data stream, the native data stream, and it's recombined at the other end. And if you happen to get more energy through multipath, so much the better. Obviously, if you have more data streams, the more data you can send from end to end. We use 2x2. There is 4x4 and 8x8 MIMO out there. And obviously between vertical and horizontal polarization, there's 90 degrees. 4x4 splits it up to 45 degrees, and the 8x8 is half of that. The issue comes up on the long haul links that we use, because 4x4 and 8x8 are really intended for, you know, local, very short haul links, is the phase jitter you get via multipath. It gets to be too much for 4x4 and 8x8. So it turns out the 2x2 MIMO and 802.11n are the sweet spot for ham radio networking. Obviously, you need a separate transceiver and A to D converter for each antenna. And all the gear we use is dual chain. That means there's 2 transceivers, 2 converters, and 2 antennas. So let's talk about LQ and NLQ. They're carried in OLSR packets. The broadcasts carry the routing and advertised services. And they have a sequence number. And when packets appear that are out of sequence, that indicates that they've been dropped. So LQ is just the percentage of packets you get from the node you're receiving, and NLQ is the percentage of packets they're receiving for you. It's reported back as a percentage. ETX, which you've seen in the column on the status page, is expected transmission count. And there's a formula there for it. Let me move this out of the way. There we go. It's not for your neighbor, but adjacent neighbor nodes, more than one hop away. For example, if your LQ and your NLQ were both 50%, you dropped half of the packets. That's 0.5 times 0.5 divided into 1. ETX would be 4, indicating a fairly crummy link. And for multiple hop paths, you just add up the ETX for each hop. So if you had, well, we'll talk about this. 1 is a perfect RF link between neighbors, no packets dropped. A DTD link, which is a device-to-device link, is an ETX of 0.1. That just gets added in. It indicates a very, very good link, as you'd expect over an Ethernet cable. When DTD is carried over a microwave link, a non-AREDN link, it's also 0.1, although you may in fact actually lose packets over that, I don't know, part 15 network or whatever. So that's kind of an issue that nobody's resolved yet. Obviously, OLSR selects the path based on the lowest cost ETX towards the destination node. And that can be an issue. And let's talk about it in a little bit. So there's another column in the status page, TXmbps, transmitted megabits per second. And you can see the formula there. The rate is the 802.11 data rate we saw in the MCS column. And it says EWMA, exponentially weighted moving average, or current time weighted, blah, blah, blah. Basically, it's the packet success rate in a decimal. Also, when you first bring up your node and you're looking at the mountaintop, all the TXmbps's are pretty close to 0, because if you've got nothing to measure, there's nothing to indicate. So you have to wait for some traffic to pass before TXmbps is legitimate and valid. So on the mesh status page, this is the right-hand column, the current neighbors. The local link neighbors, you can see, are DTD links, and they're 100%. If you have a DTD link, or sometimes a tunnel over here, TUN, and any of these are not 100%, something is drastically wrong. We saw that during packet storms up until last year, when they rolled in the packet storm fix. If it's an actual local RF neighbor, this is the TXmbps, the modulation rate times the percentage of packets. For instance, mine is 57.8 megabits per second. I'll talk about it here. LQ and NLQ, because the way they are generated and measured, are pretty low bars for success. If you can't get up very high, approaching 100%, there's something you need your RF link needs work. And the other thing about LQ and NLQ, and this will impact later, when traffic is flowing, they drop, which is not really legitimate. If you're flowing traffic successfully, they probably shouldn't drop. It's a design issue, and we'll talk about that more. On the left-hand side, these are, at the top is your local host. That's just the one you're sitting on and showing its services. But below that is the remote nodes. These are the ones that are more than one hop away. Obviously, ETX count lower is better. And here's something that a lot of people don't understand. It was pointed out to me by Joe, AE6XE. If you have 5 hops of value 1, that's an ETX of 5, but it's a perfect link. But if you have 1 hop of ETX 5, it's junk. It can't be used. So it's useful in general. Low is better, but it can be deceiving. I just threw this here as a gotcha. On the setup page, basic setup, you've got a distance setting. And they threw in auto a couple of years ago, and it works pretty well. But typically, it's only for Hilltop nodes that see multiple users. It will measure their transmission times and set it out to a little bit beyond the farthest one. And that's what auto's used for. It doesn't work well for short distances. If you've got a node that you talk to a lot that's very close by, set the setting. And here's why it's important. And by the way, all this stuff is in the help page on your node. There's a little thing that says help, and there's a ton of information in there. Let's assume you're 10 kilometers away and you set it to 8 kilometers. If it's a good strong link, you probably won't notice anything. But if you're dropping a few packets, well, let me rewind that. If it's 10 kilometers away and you accidentally set it to 12 kilometers, it'll work. But if you're dropping packets, it will wait too long to request a retransmit. You're wasting bandwidth and slowing down. On the other hand, if he's 10 kilometers away and you set it for, say, 5, it won't wait long enough, and you get a lot of retransmits and very poor throughput. So send it to the most remote RF node plus a bit. All right, we're going to talk about OLSR version 1. It's very susceptible to route flapping, and I'll explain that. So mesh networking with it is problematic. And matter of fact, AREDN has started to de-emphasize the mesh part of it. OLSR still works fine for route detection and things like that, but for alternate redundant routes, not so much. I tried to do some graphics with this, but my graphic skills are lacking, so we'll just talk about this. Here's a generic network. Let's assume node A wants to send traffic to node F through nodes B and D, but it also has a second path through nodes C and D. And you can see that the upper path with an ETX of 1.8 is the preferred path. So that'll be the path node A takes when it starts transmitting data through here. And the data is flowing fine. That's a reasonably good ETX. But because the way LQ and NLQ are designed, this ETX starts rising because you're dropping LQ and NLQ packets because they're just a broadcast protocol. Well, as it gets up to greater than 2.0, it detects there's now what it thinks a better path here. And it switches over here. That act of switching takes quite a few seconds, if not minutes. During that time, no data flows. So it establishes the link down to ETX 2.0. And once it's done that, this ETX starts dropping, this one starts rising. When this one rises above this one again, the route switches again. That's route flapping, and it will go on and on and on. And you can imagine how much worse it would get if node B has a path to node E and C, and node D has a path to node C and node E. So at least locally here, we discourage meshing. What we do is create hub and spoke networks again. You create a cell on the left using channel A cell on the right using channel C, and you link them together with yet another independent channel, channel B. And here's the cellular concept. Got two hilltops linked together with channel C as a backbone, goes on with channel D. The community on the left of the left-hand mountain is service channel A, on the right is channel B, and on the right of mountain on the right is channel A again, reusing it, as long as you're sure that none of those stations on the left will hear on channel A will hear the stations on channel A on the right, because that would create a loop. Now, if you have multiple paths that are substantially different in end-to-end ETX, you can get away with mesh, but inevitably some of those paths will be very close in value, and you will get route flapping, and your network will come to a screeching halt. Ask me how I know. Okay, here's a practical example. This is a map of an area in Central California, about 250 kilometers northwest of here, centered around the town of Paso Robles, which is inland, I don't know, 100 kilometers or so from the ocean, Pacific Ocean. And I've gotten the Central Coast guys all excited about mesh networking, or ham radio networking, I should say. And I'm helping them with doing some planning. The little tower image on the left is W6RR, Radio Ranch, and it is in fact a radio ranch. He's up on a nice hill with lots of areas. He's got 2 or 3 ham radio towers and a big honkin' cell tower, and he charges the wireless carriers out the wazoo, as we say, for renting space on his cell tower. So he's got a fair amount of cash to throw into ham radio. And I gave a presentation and to the group up there, my overview presentation, and they jumped in with both feet, as did he. And it turns out they have a lot of spare equipment and they're throwing cash at it, but I'm helping them with network planning. So you can see this as anything but flat land. It's hilly. W6RR has offered to cover, put some gear up to cover this whole area. Paso Robles is the largest town. It's not huge. And by the way, if you're ever in California and you're a wine connoisseur, there are excellent wineries up and down here, Atascadero, Templeton, Paso Robles. It's renowned. So anyway, we decided that what we would do is put a 120-degree sector antenna pointing east from Radio Ranch there, which covers all of Paso Robles. And there's some smaller communities not shown in the pink area. And by the way, when I did this, I told it to limit the emissions out to 25 kilometers, when in effect, with decent antennas on each end, you can probably get out to very close to 100 kilometers. So anyway, I just limited it for that. So anyway, that's the eastern looking, but we're still not covering Templeton, Asuncion, and Atascadero down here. So we'll add another sector antenna pointing that way. In this case, a 90-degree sector would have been better, but in the a surplus of WISP antenna that was bequeathed to the hams there, they had all 120 degrees, so we'll use what we have. So here's another real-world example. This is my area in Ventura County, which is northwest of downtown Los Angeles by, let me do the conversion, maybe 75 kilometers. And you can see it's moderately hilly with some hilltop sites and some valleys. The red stuff spans about 70 kilometers, I think. So anyway, you can see the red is where we've established our backbone. What else? Oh, the blue in the center is my 3 gigahertz local backbone that links 3 hilltops surrounding my city. So I'm fortunate to be able to cover the valley that way. I just threw this in here. The AREDN code is based on OpenWRT, which is based on Linux. So all the Linux commands can be used at the command line. Once in a great while, you'll see one of the devs talk about some extra information, typically about the wireless stuff you can't see on the UI, but you can see it with commands on the command line. So in order to do that, you have to SSH into the node that's secure shell. OpenSSH is the package. It's integral to all of the Linux packages, Linux distributions. On Windows 10, you have to install it, but it's easy. You go into optional packages. They're supporting it quite well now. And you open up a command and you invoke SSH. And up here at the top, although this is a Linux box, you can see the command is the same. Typically, SSH uses port 22, but for whatever reason, AREDN and its predecessor, Broadband Hamnet, chose to use port 2222. Maybe it was security through obscurity. So anyway, do SSH to root, which is the only account on a node, and then and then the node name, and you get to the prompt down here. I'm not going to list all the commands are available. That's a whole nother 3 or 4 presentations. But just know it's there. I would install OpenSH and know how to do this. It's kind of fun to poke around. Okay, some equipment discussion. Ubiquiti nanostations have been popular for, oh gosh, since they started supporting them 6 or 8 years ago. 6, let me think, 2015, 14, 8 years ago. Good for up to 10 or 12 miles. I didn't convert that to kilometers, but you get the idea. I'm not recommending them for new purchases. What we found out, we did you may or may not have heard about it. Over here on the West Coast, Southern California particularly, we had been plagued by what they call network storms or router storms. Masses of packets circulating around the network for, oh, I don't know, anywhere from 10 minutes to half a day. Really impacting the scalability of the network. There was a guy up in the Bay Area who's a coder. He started 3 or 4 small startups, got interested in ham radio networking last July, and got his ham radio license specifically so he could work on the code. As Tim, KN6PLV. And he captured some packets, looked at it, wrote up a paper on what he thought the problem was, and coded up a fix. The AREDN guys weren't ready to put it out in a nightly build, but another ham local in my area happens to be one of the coders. He coded up a special version including that. We tested it for, I don't know, 6 or 8 weeks and didn't see one storm. So we turned that evidence over to the AREDN devs, and they decided to put it in a nightly build. And we encouraged people to roll it out. And it's kind of like a vaccine. Not everybody needs it, but the more people, the better. And then they started doing it up in the Bay Area, San Francisco Bay. And we decided to run a stress test. So we linked everything together we could last Halloween, called it Meshaween. And I think the packet count in a couple of areas got up to 1,500 nodes. And while the network did just fine, we discovered that these older nodes kind of buckled under the load. Part of it is the fact that they are using the oldest CPU of any of the gear. that AREDN supports, 400 megahertz. Tim did a deep dive into the code and found some inefficiencies in the Perl code that displays the UIs, and he submitted, I don't know, 10 or 12 patches in here and there and fixed that. However, they're still old and slow. Here's a nice replacement, the Microtic SXT Sq for 2 and 5 gigs. About the same game, same distance. They're about 20 centimeters on a side, so they're not very big. And I want to mention that that mast clamp you see on the right is an optional clamp. Otherwise, you just get to clamp it vertically on a pole. Nice thing about these is the CPU is 50% faster than the Ubiquiti NanoStation, so you're kind of future-proofing it as your network grows. Talking about links, those are good for short haul. These will probably be better out to 50 kilometers or so. The Ubiquiti PowerBeam in 3 various sizes, and the Microtic large head grid in 3 flavors. The PowerBeams are starting to get scarce. Ubiquiti is starting to or already has stopped producing their 802.11n only versions, and they're now shipping versions that are 802.11 AC backwards compatible to 802.11n. We'll talk about that some more. The Microtic dishes are popular with those who are building portable setups, either Go boxes or standalone digital Go boxes, because they're quite a bit lighter. £1.5 pounds, I think. The only gotcha for these is if you live in an area that has heavy icing, you might want to pass the Microtics by, because that's a plastic hex grid for reinforcement behind the screen. Might not be as durable with ice on it. TP-Links work really well. I don't know why they're not as popular as they are here. 210, 220 are 2.4 gigs. CPE 510 is 5.8 gigs. They have more RAM. I'm not sure what the CPU speed is. CPE 610 is for 5.8 gigs. It was discontinued about a year ago. It's on, you can find it on eBay. Works very nicely. CPE 710 is the replacement. AREDN is rolling support for it, and I will talk about that later, but it should be later in this year. So this is the little box that every ham radio networking guy running AREDN Code should have on their desk, and I talked about this before. The AREDN Code uses the 10.0.0/8 network, the Class A private network, and it can't be changed. They're hard-coded in here, which makes it difficult to integrate with your home network, which is probably 192.168. something. Well, if you put this device in between, it nicely integrates the two and lets anything in ports 2, 3, or 4 talk to both the mesh network and the home radio network. And yes, it's nicely firewalled in between. If you're talking about building backbone equipment for longer haul, the Ubiquiti Rocket M5 plus the Rocket Dish are the heavy-duty commercial versions. You could use a PowerBeam for shorter distances. This is what we prefer. Again, the Rocket M5s are still available, but you know, you can spend 220 pounds. I converted that from the dollars I found. For the shorter links, I'm starting to recommend Microtic QRT5. The dish on the left is about 30 dBi gain. The one on the right, the panel there, is 24 dBi. The one on the left has about a 5-degree beam width, and on the right is 10 degree, but should be great for short haul. The Central Coast, California Central Coast guys were bequeathed a double handful of the QRT5s, and their links tend to be shorter. So I'm recommending they recycle those and put them up on mountaintops. So what's AREDN got going on in 2022? I got admitted to the inner sanctum as an observer a few months ago. So I have had my ear to the wall. And there's nothing private here. This has all been published. For whatever reason, when Broadband Hamnet wrote up their version of the code, they used Perl, probably because the programmer knew Perl. Well, the libraries are pretty bulky and they take up a lot of room. So they've decided to migrate the code to something called Lua, which is designed for embedded devices, and consequently it's quite a bit lighter. Initially, they're going to update the read-only pages to Lua, and the latest nightly builds have done that. If you're running a late nightly build, the read-only pages are written in Lua. Sometime in the next month, 6 weeks, they're going to update the read-write pages. They're obviously more complex because they're not just displaying data, and it's all of the other pages. Next step is OpenWRT periodically puts out new releases, and the AREDN base code has to be rebased on that. And this one's fairly significant. Multiple physical interfaces, because the Microtic radios have slots in them for PCMCI, I think that's it, PCMCIA radios. You could have two radios in the same box, and they have to be able to account for that. They'll have to roll that into the AREDN displays. You know how some of our AREDN software installs are ATH71 or AR71 and ATH79 or something like that. That's because they're midway in the process of transitioning all the drivers over to the newer one. So you'll see more of those. API updates, all the Lua stuff. And once that's done, they'll start migrating in the 802.11 AC drivers. I'll fix that. And as actually, once 21.02.1 comes in, the drivers will be there. However, they only accommodate 20 megahertz bandwidths. So you could, for instance, load up a CPE 710 with AREDN in the ham band, but only 20 megahertz. If you want 10 and 5, you're going to have to wait a little bit, because those flavors were developed separately because they're not used in your typical OpenWRT Part 15 wireless device. So those will come along. But the coder, Joe AE6XE, feels fairly confident that we'll have maybe a couple of handfuls of those in nightly builds by late this year. New user interface. Lua is designed for supporting user interfaces, much easier to build modern interfaces and modify them as you need. So that'll be coming later on. I've talked about the problems with OLSR v1. The developers deprecated it a number of years ago and went to OLSR v2. It also had its problems and it was deprecated. So they're thinking about migrating to Batman. Better approach to mobile ad hoc networking. There's a nice description of it in Wikipedia. Unlike OLSR, which is layer 3 routing, IP routing, Batman is layer 2 routing at the MAC layer. So you have to add your own layer 3 on top of it, which might be the OLSR 10.0.0, or I've floated the idea of using 44net addresses. You know, because Amper owns some ham radio, some IP address ranges in the 44 network, actually all of it until recently, intended for ham radio use, and it's been underutilized. I think there's only one other ham radio network that's using 44 addresses. And getting that implemented into a nightly build and figuring out how to work it is going to be pretty challenging. And what's worse, none of those are backwards compatible. So my plans, I don't know how it is in your part of the world, but our microwave bands are under attack by the carriers, and our business leaning FCC is not helping things. We lose half of the 3 gig band in March here, and the rest of it is being looked at very closely. And just recently, we've always been secondary in the upper half of the 5 gigahertz band. Our Department of Transmit Department of Transportation was secondary, excuse me, primary, but they never did anything with it, and the FCC kicked them out late last year. So now they're letting WISP's license in there. So I expect the noise levels to go up slowly there. And since we're secondary, we have to accommodate them. That being said, to future-proof your setups on a hilltop, design in more gain than you think you need at the moment, because the noise levels are going to come up. As part of that, I'm going to look for a microwave designer I've started to make a 5 gig to 10 gig transverter that we can slap on front of a Rocket M5 or a Microtic, I think it's a bandbox. Anyway, they're 5 gig MIMO thing. I sat in on the ARDC community meeting yesterday morning, and it sounds like this would be something they would be happy to fund the development of. Alternatively, I'm going to ping Ubiquiti and Microtic and see if we can persuade them to modify their 11 gig gear down to 10 gig. This will help for point-to-point, but I don't expect it will be affordable for the average ground level user. But I do infrastructure, so it's near and dear to me. Q&A feedback. What do you think, guys? Too much of something, not enough of something else? Any comments? If not, I'll go fix my typos.
This is Art.
Slide. Yeah.
I really enjoyed it. We're at the beginning of trying to put together a mesh network, AREDN network in the St. Louis area. And I've been playing around. I'm not a network designer by any means. So your list of equipment, I really liked the slides that said, you know, move away from this one, because I do have the Ubiquiti M5s, and to move toward this. So that kind of information was very helpful to me.
Very good.
Some of the deep dive is way over my head, but the other stuff I found very good. So thank you.
Good.
Are these slides going to be available to us?
I will make them available. Just remind Andy or John to ask me or remind me about it.
Okay.
Typically on something like this, I do a lot of talking, and the slides themselves aren't much good. So I make a PDF version and I put all the verbiage in it. So, and you talked about recommended equipment.
Yeah.
On the AREDN website, there is a product supported platform matrix, and they have flagged all the devices that they don't recommend for new deployment. Okay. You might want to look that over. They have not flagged the NanoStation there yet, but I'm going to start telling them that should be flagged because of the slower CPU.
Okay.
But yeah, that'll be available.
Great. Thank you.
I'd just like to thank you for a most interesting resume of the system. I'm an 82-year-old, so basically so much of it is above my head, but I like to think that I keep in touch with what is going on in our hobby. With over 60 years as a licensed amateur, seen so much change. And it's good to see that the hobby is being carried forward into the future, because I think the younger folk now who need to look at our hobby will find all of these developments very, very interesting indeed. So I thank you for that, and for your time in giving the presentation. Thank you. You're
very welcome, Peter. Did you happen to sit in on my first presentation?
No, unfortunately, I missed that. But,
okay.
If that was going to be repeated, I would certainly like to see it again sometime, maybe later in the year.
Well, if you search YouTube for W6BI and AREDN, you will find a number of my presentations out there. Not this one. This is the first one of this type. But I will mention something I did mention there, and it'll tie in with Colin's question asking about BGP. AREDN evolved from the standpoint, the philosophy of making something that was easy to deploy in an emergency. A typical ham radio operator isn't super knowledgeable about networking and having to set up a DNS server and a DHCP server and allocate routing like BGP or some of the others, was not part of their philosophy. So it was designed to get working easily. Now, some of the other networks like HamWAN do use traditional networking and BGP, but that's a high-end fixed network. It's not meant for ad hoc networking. Now, AREDN's outgrown the ad hoc networking stuff, so we have to deal with what we've got. But with several thousand nodes on the network, at least, it's been fairly successful. And I hope to keep educating you folks so you can get up on it.